very kind introduction, and we'll get slowly set up. Look, one thing I can say is it's really great to see, bipartisan political support for science, I think, in New South Wales, because some of the results that you're about to see in this talk are imperiled by the cuts that are sort of about to happen in the United States of many of my colleagues who work for NASA. So, it's something that we very much hope doesn't happen here. And so I'm very optimistic. Anyway, look, I'm going to be talking about, actually, I'm sorry, I left something back at the table. Give me 1 second, I've got a prop. I've got a prop to pass around, right? I'm actually going to show you the only Australian hardware on board the James Webb Space Telescope. This is, I'll give it to the minister first. Please do give it back, we've only got one of them. This is actually a prototype of the only Australian hardware on board James Webb, and this will be sort of the subject of the talk, is how we're using this. And so this is something which I'll show you is going to shape light in such a way as we can get sharper images from this telescope, which harks back, and I will digress during this talk about this interesting historical point, it harks back to a technology developed in Sydney on the cliffs above Bondi, by Ruby Payne Scott in the 1940s, which has been really an area of Australian leadership, a technology called interferometry. So, first of all, exoplanets. What's the deal with an exoplanet? Okay, exoplanet stands for extrasolar planet, that is a planet around another star. Okay, when I was at school, the textbook said that we didn't know if any of such existed. That was because they take a little while to print, because in fact it wasn't until I was 5 that the first one was discovered in 1995, 51 Pegasi b by Didier Queloz. And what's really quite cool is there's something like, who's heard of Moore's law for computing, right? The power of computers doubles every 18 months, for a given cost. Something like that applies to exoplanets too. In fact, I think this is a hallmark of almost all really successful sciences at the moment, is that something like Moore's law applies. So the number of exoplanets known doubles every 27 months. So back when I found 145 exoplanets in my PhD, that was a good number. Now it's Wednesday. They're really rocketing up. And this is something that's true also of DNA base pairs. You can sequence more and more base pairs for a given cost with time. Things like that. This is a hallmark of a science that's really exploding, right? And so one of the things that's sort of happening is many technologies are being developed for detecting exoplanets. And I'm going to say something slightly controversial, is that the old technologies for detecting exoplanets are now boring because exoplanets are so easy to find. The issue is not finding them now, the issue is understanding their physics. So what's really important is that we can't just say, oh, there's a planet around that star, that's great, is that we actually can say the planet has this kind of spectrum, and this spectrum then tells us something about its atmosphere. Could there be life? What geology does this planet have? What does this tell us about the geological processes by which the Earth or the other planets in our solar system formed? And so what I want to do is directly image planets. And so when I said, oh, we found 145 planets in my PhD, that's nothing these days. Well, people haven't found that many by direct imaging at all. Direct imaging is hard. So here are some videos. My colleague Jason Wang produced some videos where you can see a handful of planets. There's one orbiting, that's called Beta Pictoris b. There's some planets orbiting. These are videos that he's taken with a special telescope equipped with something called a coronagraph. Now the trick is, this is a technology for blocking out starlight so that you can see faint planets next to the stars. The planets are very, very much fainter. The Earth is 10 billion times fainter than the Sun. So you need to block out the glare of the starlight, and all this scruff you can see around the star, which has been just blacked out in the image because otherwise it would just be completely saturated. That scruff is not like cool space stuff happening. That's just light inside the telescope being scattered because our technology is not perfect. So at a high level, what I'm trying to do is develop better technology for doing this, to get down all this scruff, because these planets are actually very hot newborn planets, and so they're very, very massive. They're many more times massive than Jupiter. They're very far from their star, so you can easily separate the light, and they're very hot because they're newborn. They've been formed in this violent process. So they're only a few thousand times fainter than their star. That makes them easy, and you can still barely find them. So what I'm doing is developing technology for doing this better so we can detect Earths, right? And so to give you an analogy of how bad this is, if the Sun were a typical lighthouse, these planets that I showed you in the last images would be as bright as fireflies next to that lighthouse, right? And they would be next to it. I actually don't have this number on there. Something like a few meters away from that lighthouse, kilometers distant, right? On the other hand, an old planet like in our solar system, Jupiter, is about as bright as an alga next to that lighthouse. So we really need an extraordinary amount of dynamic range in these images, right? So we're using the James Webb Space Telescope, which is this $10 billion NASA mission. It's the most expensive ever individual scientific mission, and it is exquisite in its capabilities. It has surpassed everything we had ever hoped for. It was delayed by nearly a decade. When I started my PhD, they were saying, oh, don't worry, you're going to simulate these data, and then by the end of your PhD, you'll have the observations from Webb. Well, I was already a senior lecturer by the time we had observations from Webb, so there we go. There is a picture of it being assembled on the ground. And what we have, and this is both a point of pride and of shame, there is only one Australian component on board James Webb, which is this aperture mask. And this is something that leverages a heritage. The mask itself is trivial. I mean, it cost a couple of $100 to make, and we got about 16 hours of web time in compensation for that, which is actually highly leveraged because it costs about $100,000 an hour to get James Webb operations. And so that, it's a pretty good investment. This is a great point of pride because what's actually, this mask is no investment at all really. It's just a small piece of metal that shapes the light. But what it really is the mathematics of designing that metal and then the software that you use to analyze the light knowing that design. This exquisite pairing of software with geometry is what this is. So, behind this mask, I want you to imagine countless hours of work trying to write software and mathematics to do this. I want to slightly digress here. One, isn't it a shame that we only have one Australian piece of hardware on board Webb? I know we're a small country, but Canada built the entire camera this is mounted on. When I say camera, I don't mean like a little SLR. I mean $1 billion, all singing, all dancing, the best camera in the entire world, right? We fitted one component to it. And Canada's not that much bigger than Australia. I really think we should be aiming to deliver Canadian-level contributions to international science missions. I know it's beyond our capacity to build Webb. That is a truly titanic affair. But to build an instrument like NIRISS, which is this camera, which is really the sharpest camera on Webb, and only deliver one instrument, I think is a bit embarrassing. But what isn't embarrassing is that this instrument is the highest resolution mode that's available on Webb. And what it is an evolution of something that was invented actually in Dover Heights, at the old CSIRO base there, which was actually a radar base during the war, by Ruby Payne Scott, who was a groundbreaking Australian scientist. The science of interferometry, arguably developed there, and is the way in which all radio telescopes operate today at high resolution. You may think, who cares about radio telescopes? I'm not an astronomer. Well, I mean, I won't bore you with the details, but I've had some health problems recently. Don't worry, I'm fine. But as part of resolving that, I've had MRIs. Now, the MRIs, all the hardware, it's very sophisticated. The mathematics behind MRI won the Australian astronomer Ron Bracewell the International Prize of the IEEE for developing a civilian application of radio interferometry, which is an astronomical technology. So I love it when people talk about the CSIRO's amazing success in Wi-Fi, but I think Wi-Fi is far from the most successful technology to have developed out of interferometry in Australia, in astronomy. MRI, right? The foundational mathematics of this, substantially developed by Ron Bracewell as a result of the early experiments in this science, right? And so this sort of shows you that it's not really possible to predict what kinds of developments will come out of science, but particularly of very abstract sciences, like fundamentally this is just applied maths, right? And this applied maths has permeated through all of our technology. Anyway, so why are we doing this? Well, I'm about to say someone who's not well known as a scientist, but well known for his other work. Immanuel Kant was the one who figured out how planets formed. I think that's amazing. He spends all his time thinking about ethics and critique of pure reason and all that jazz, and then takes a little break, does some astronomy, and casually figures out planet formation. He argued that because the planets in our solar system orbit in the same plane, and he did some calculations and some sort of arguments to say they must have formed from a cloud of collapsing gas and dust, which is flattened into a disk by its rotation. And so he called that an Oort nebula, an Oort cloud, right? And for 200 years, people didn't know if these were real, but it was certainly a very nice idea, right? And then only about a decade ago, I remember when this image dropped. I was a PhD student. This must have been 2012 or 2013 or something. HL Tau was the first one. So we just see these now with an interferometer in Chile. And so one of the things we're asking to do as an Australian astronomy community at the moment is to join as members the ALMA consortium, which takes these images, which is currently the world's best interferometer. And so this is a disk, right? And we're seeing this dust. We're seeing these dark lanes carved into the dust. And these dark lanes are where planets are sucking up the dust and clearing out their orbits, right? And so what I want to do is image the process by which this is happening, right? So here's a system my colleague Sebastian Haffert discovered called PDS-70. Astronomy things, people think they're going to have really cool names. It stands for Protoplanetary Disk Search number 70. They were searching for protoplanetary disks, and this is the 70th one they found. But what's really cool is you can see there's a little orange dot inside the gap in this ring. And if I really rammed up the color scale, there's actually 2 dots, but it's sort of hard to bring out to the eye for an audience, right? There's another one sort of down there. On the right, what we see is contours overlaid of where hydrogen is being shocked. Hydrogen's reaching extremely high temperatures in 2 little spots, which correspond to these little dots inside the ring. What that's telling us is that gas is falling violently onto a core. And so that's where we estimate that Jupiter mass planets are being born, right? And so the hydrogen emission, these contours, it's a little bit hard to sort of see what I mean, these contours, that's tracing where hydrogen is being heated to extreme temperatures by falling onto proto-Jupiters, right? So what I want to do is take infrared images of this so I can see what temperature all the dust is, what's its geometry, what's going on there, right? So in fact, in compensation for delivering the aperture masking interferometer, we were awarded time at about 100 grand an hour, 16 hours, so that's good. It's a couple of apartments in Sydney. We were awarded time to observe 4 such systems. PDS-70, where we know this is happening. 2 others where we suspected it was happening but haven't detected it yet, and James Webb should have the capacity to do that. And another one where we knew it had happened and we were looking for the debris. Really stuff like the asteroid belt in our solar system. Except the trouble is, James Webb's perfect in almost every way, except it's slightly blurry for bright objects. This is called the brighter, fatter effect. So if a bright thing gets blurred out, so it looks fatter on your detector. And so Eta Corvi, our observations were useless. And so there began a journey which has been challenging for me and more challenging for my PhD student, Louis Desdois, who's been very, very hardworking and talented, trying to figure out what's going on, right? And so we're using this interferometer not merely because it allows us to have sharp resolution, but because it allows us to have exquisite calibration. Because these detectors, which are H2RGs, doesn't mean anything to you, but this is the foundational technology. It's called a mercury-cadmium telluride detector. This is the foundational technology by which all thermal infrared cameras work. So anytime you've seen, God knows, I hope not some military video, but certainly something, animals on the Serengeti, or when people look at, termites in your building. We recently, we're trying to buy an apartment, building and pest assessments. They get out these thermal cameras to look for damage in the building, right? They all use these, and they're all slightly blurry for the same reason. It's called the brighter, fatter effect. And so what we had to do was to try and figure out a computer way to fix it. And I can tell you that we have. We're the first to have figured out how to de-blur these cameras, right? And so we'd love to try and commercialize that. Technology. So there's a lot of scientists here, and there's a lot of probably science nerds who love to say in television shows, people will be like, oh, computer enhance on the picture of a suspect or the number plate or something. And many people, including one Nobel laureate, have told me that absolutely you can't do this. Information theory says you can't. No, there's no way a computer could do that. And that's absolutely not true. It turns out that this is a process called deconvolution, that you totally can de-blur images, right? But what you've got to know is the process by which they were blurred and the kinds of image that they might be, right? And so when you blur something, you get some guy, and then you've got some image gets blurred. This is a mock-up I had of what a telescope looks like. You get some blurry output, right? This is a mathematical process called convolution where you run this little pattern over the whole thing and you smear it out that way, right? And so it turns out this pattern is generated by a certain mathematical operation on what the aperture of your camera looks like. It's called Fourier transform, and you can go from that to this blurring kernel, we call it, you know, which is what a star looks like through that and what runs over your image to blur it out. Now, the trouble is, you have to de-blur it. This is an inverse problem. So statistics isn't about, everyone's like, oh, what, you teach statistics. You know, what does that involve? It's about numbers. No, it's about inference. It's about how do you learn something from data. It's not about means and standard deviations. Those are tools. It's about how do you go back from data to its causes. Everyone likes to say, oh, correlation doesn't equal causation. No, but correlation plus a model does. And so you've got to have that model. Even worse, your telescope can have all these mirrors get bendy and misaligned. And so you don't even know what this sort of, we call it a point spread function, you know, this image looks like. This is a classic problem in science called phase retrieval that crops up everywhere. I recently went to the Victor Chang Institute, and they had an X-ray diffraction experiment, you know, mapping out a protein for a medical purpose, right? Exactly the same physics and exactly the same maths of phase retrieval. It's how you go back from these data to a map of the protein or to a map of your telescope or whatever, right? The other thing that you do, so you need a phase retrieval algorithm, is you need to know what sorts of image you're looking at. So the reason you can de-blur number plates is you know they're black and white, or yellow and black or whatever, and they have numbers and letters, right? And you can de-blur images of suspects because you actually know that human beings, you know, have certain regular patterns that they look like. There's only so much dimensionality to what humans look like, right? And so you can take a few pixels and you can go, well, actually, I can figure out someone's hair color, skin color, maybe their gender, are they wearing glasses, do they have a beard, all that sort of stuff from only a few pixels, right? And therefore, you can actually get a good idea of what someone looks like. That's the trick, is if you knew it was a completely arbitrary image, you wouldn't know if it had hair and beard and glasses at all, right? You know, it could be a cat. But if you know it's a human being, you can actually figure these things out, right? So I want you to sort of have a little look. Let's have a show of hands. I've used generative AI to make an image of a real galaxy and had also an image of, you know, a fake galaxy that I made up, right? Who thinks the real galaxy is A? Who thinks it's B? Okay, well, you're all scientists, you're right. It's B is the real one and A is the fake one, but not everyone gets that when I give this to other audiences, right? What we can actually do is build a statistical model of what images look like. This one's called a diffusion model. So this is what Stable Diffusion uses. This is what ChatGPT or Google, Gemini, or whatever use. This is a statistics model that actually the Australian firm Leonardo AI is building for Canva, is actually a world leader in this. We're collaborating with them to try and figure out how do you build a computer model of what planets and galaxies and stuff look like, right? And then you can use this in place of this idea of what your suspects look like to try and help you deconvolve images of astronomical scenes, right? And so this aperture mask, it's looked like that. It's installed in the telescope, right? And it gives you these data that are basically a video. I assure you, for those at the back, this is a video. It's just extraordinarily stable. On the right, I've got the differences of each frame relative to one another. And what we see is that the frames get more and more different as you accumulate light in this exposure. We've actually got a video just continuously accumulating light, and they're getting blurred out by this brighter, fatter effect. So what we've done is we've developed an optical simulation tool which is compatible with modern AI. What makes it compatible with modern AI technology is it's written in the same language. So we use something called JAX. There's really two industry standards. There's JAX or PyTorch, if anyone's a computer scientist here. We picked one of them. The difference isn't important. But the important thing is that a take-home message is if you are working on computational science or physics or something, if you write your code in JAX, it will talk to any of your AI tools, and you can fit models in very high dimensions with great complexity very, very efficiently, which would be totally impossible otherwise. So what we're able to do is to sort of simulate, because we can simulate, given a model of the distortions on our telescope and all the electronic crap that's going on, we can simulate what this video should look like. And then we're able to go back from that video that we've observed to you are some of the first people to see that, this is an image of PDS 70 as seen by James Webb. So this beautiful sharp image in which these two dots of planets are clearly visible, in which this arc, which is brightened on one side, is visible. And this is allowing us to map out the temperature of all the dust around these planets. And actually there's some problems that we don't really understand why one of them is as bright as it is. It's actually accreting a lot more than we expected. And this is sort of a great test case for what we'd like to roll out across a lot of James Webb observing programs for being able to get this really high resolution imagery really efficiently. Right? So here's the same image but overlaid on this other image, and you can see that we're mapping the hotter inner part of that dust. Right? Anyway, look, thank you for coming. And do you have any questions?
We'll hold it at the end.
Hold it at the end? Easy. Good. See you later.